Why you don't see much of BJT, yeah, the bipolar junction transistor in RF applications? The reason is this: bipolar, as the name says, it has both P and N kind of dopants into them. It has both P semiconductor and N semiconductor. That means it has both majority and minority carriers in them. So it's bipolar in that sense. But predominantly, it's a current control device. We see that your IC is going to be beta times IB. So depending on IB, your IC is controlled. So it's a current controlled device. If it's a current control device, it should at least accept IB in the first place. That means it's a low input impedance device. That means it's going to be drawing IB current into the transistor. Because of that, since your IC is high, you can achieve high voltage gains there by simply having a resistor there. The drop across the resistor is going to be the voltage. Since IC is high, the voltage is going to be high as well. However, the key challenge with BJT is that it has a medium switching time going on and off. There is some transients that it is capacitive effects inside the junction itself, that it is not going to allow you for fast switching applications or fast moving signals, which is what going to be the case for RF applications. So it is not used in RF, but it is used for sub gigahertz. That means less than 1 gigahertz. The frequency is less than 1 gigahertz, then BJT can be used. However, the other counterpart that we are looking at is called as a field effect transistor, which is a better transistor more suited for RF applications because of being monopolar in nature. That means it either has the P, the holes, or the electrons as the carriers. It's a voltage control device. That means it is the gate voltage. It is the gate voltage that controls what is the drain current. Unlike this case where it is the base current which controls the collector current. So it is a voltage control device where it is the gate voltage that controls the transistor, whether it is on or off. So there is in fact no current flowing into the FET. It's going to be very low. That's why it is a high input impedance device, which means it can be operating in a low power regime. So it is not even taking any current in for the switching to happen. So that's a big advantage of FET. However, the compromise is it's going to be a low voltage gain device, but it is going to have fast switching times. So it is going to be widely used in RF and being pushed even further. The third kind, which is widely used in RF more than even FET, is what is called as high mobility, high electron mobility transistor, where the electrons are free to move even faster. So you can go up to frequencies even gigahertz, and people are talking about terahertz. So the idea is to have a channel with two different materials. That's the main difference. It's a heterostructure. That means it's not a unique semiconductor material, but it's going to have two different channels, like what you see as gallium arsenide here, and the different layers of the semiconductor material there.